Alright, here we go, folks. Oh, I don't have my equation up now. Alright, so number 3 was requested. How much work is required for a runner to accelerate from rest to a speed of this? Stretch answer. Alright. So, back here we have our energy bar graph, which will be our Y. And let's see. Since they're moving, there's going to be kinetic energy. What about potential energy grab? Do you think that's involved here at all? No, I didn't have it all. What about potential energy spring? No, I didn't have it either because there's no spring. So, I'm looking at the initial situation, which is that they are standing there, because they're at rest. And so I'm going to draw in their kinetic energy here at 0. Then there's some work done on them, and it's going to be external work. So I'm going to grab a square, pick a pretty color, and I'm going to say there's like that. How that works. See if I can change the size of the
63.
I'm not letting that okay, maybe a different one. Try that. That's better. So I'm going to say that that much external work was done, and if that much external work is done, then that's how much kinetic energy is there also. Maybe I'll just make it pretty and change the colors. And that would be a full credit Y for that problem. How many people got that? Excellent. Excellent. All right. So now I'm going to use that as my starting point, that the work is going to equal the kinetic energy. So right here on my how, that's where I'm going to start. I'm going to start with the work. What's going on here? Try this again. So I'm starting off with that fact that my work equals my kinetic energy. So maybe I should grab something for work. Well, let's see. Let's go back and look at the problem. How much work is required? Okay, so I don't even need an equation for work. I just need my equation for kinetic energy, which I can grab from here, right? Grab my kinetic energy equation here. And I heard someone making the most common mistake that will be made. They'll forget the square term in there.
Oh.
So I've got 7 meters per second. So I'm just substituting in here equals 1/2 I think I was 68 kilograms. Oops. 68 kilograms. And 7.0 meters per second squared. And of course, 3 sig figs, and because I'm in kilograms and meters per second and everything, I'm going to end up with joules. So whatever that ends up being. I got 1,666, which of course 3 sig figs will give me 1,670 joules. And that should be right. Let's see. 1,670. Yay! Alright, so number one, a Tron entry has used a rope attached to a bucket to lift a 27 Newton dog. Ooh, 27 Newtons. Is that the dog's mass or the dog's weight? Newtons, measure of force. So it's the dog's weight, which is the force of gravity. Upwards through this. So, alrighty. So I'm going back here, and I'm not really worried. The dog, I'm going to assume, starts at rest and gets up to the treehouse at rest. I think that I'm going to use some PE grab here because the dog's moving upwards. So I'm going to put that in here. PE. I wonder if this is. And then grab. Subscript. It's a little large, but you get the idea. Alright. So looking at our situation, I'm going to call the ground 0 for PE grab. Is everyone okay with that? That's what I like to do. And then, and they're doing work on it, and all the work they're doing on it is going to go into PE grab. So I'm going to do this, pick a nice pretty color. They do a bunch of work on it like that. And then that's all going to go into PE grab. And there's my full credit Y.
Yes.
Excellent. And then again, I'm going to start at that exact same point. See if the board likes me this time. Right? The work this time is going into PE grab rather than kinetic energy.
I think so.
So I'm going to grab my equation for PE grab. Yeah. Yes. Yep. Paste that. Grab that. Alright, so let's do this. Now what's nice is they gave me the weight of the dog, right? And we know that the weight of the dog is mg, so I can just put in that 27 newtons. So that is my mg, the 27 newtons, and then my height is 5.0 meters. Let's see, 5 times 20 is 100, 5 times 7 is 35, 135 joules. Let's see if I got it right. Oh, they want 2 sig figs. So that would round that up to 140. There we go. So they wanted 2 sig figs rather than 3. Pesky book. Alright, so number 6. Player passes a fastball down court for fast break. Ball leaves player's hands this speed and slows down to this at its highest point. Including air resistance, how high? Ignoring air resistance. Good, no dissipated force. How high above the release point is the ball when it's at its maximum height? So since there isn't any air resistance, I know that it's a closed system. What's the other thing in the system besides the basketball? The ground. The person was until they released it. We're going to consider that once the ball is released, that's when we start looking at the situation. So at the beginning, it's going to have some kinetic energy because it has that speed. The system is it and the ground, and then it slows down to that speed. So since the ground's involved here, I'm going to have some PE grab. We can do a smaller text size this time, maybe. So I'm going to do some PE and then grab here. Again, no PE spring because I don't see a spring at all in the problem. Going to have some kinetic energy to start. Give it a bunch. And then it's going to have less kinetic energy afterwards, right? And what happened is that some of that KE has gone to PE grab. So I'm down 3 here. So 3 here. No external work because there's no air resistance, or God didn't come down and push it with his hand, or someone didn't catch it and rethrow it or something like that. Yeah. So yeah, that would be it. Kinetic energy at the beginning, some kinetic at the end, potential energy grab. So I'm going to use that right at here. So I'm going to start off with that equation. So KE, and because that one's before anything happens, I'm going to call it initial. I'm going to put a lowercase I there, equals KE afterwards, which I'm going to label as final, plus PE grab final. I could have a PE grab initial, but we are going to consider that point to be 0. Is that okay? Then I just have one less term to write, but I could have that on the left-hand side also. grab some of my equations here. I want to know that final height, so, ooh, I think I already have that. Good, so I can paste that in. And then I need my good old friend kinetic energy. Alright. I'm just going to put the values in my head, so I'm going 0.6, 8, 10, and 7. So, so 1/2 mass of the ball, speed of the ball initially squared equals 1/2 mass of the ball, the final speed of the ball squared, plus mass of the ball times the gravitational field strength on this planet times the maximum height. Oh, I can do a little algebra to save myself some work, right? So I could get rid of all the m's. Then I don't have to worry about grams and kilograms. And now I just substitute in, right? 1/2, mine was 8.1 meters per second, equals 1/2, 7.00 meters per second, plus this planet is 9.81 newtons per kilogram, and then h, because it's always good to have a variable when I want to solve for something. And let's see, meters, seconds, kilograms, newtons. Oh, I'm going to end up with meters. That's good. And I got 0.846 meters. Let's see if I got it right.